whatever we discussed last time. So we said we wanted to study about data. Why study data? And we saw that because now is the right ecosystem to study data. Then we talked a little bit about statistics and mathematics and also about data science. So we'll recap what we did last time and we'll look at some tools to study data and what exactly is data, what are the types of statistics and the data life cycle. So let's see how much we cover today. The rest we'll cover in the next section. So we discussed that why do we need to study data? Because now we have huge amounts of data and data is called the new oil in the economy, which is just making the economy run. So, but data is just a number and we have to make sense out of the data. We have to draw inferences out of it. We have to draw conclusions out of it. And why do we need to do that? Because we want that to aid our decision making. We also looked at how data would be the raw data, and we'll study further what do we mean by data, what are the types of data. And we want to transform data into some kind of information. What can I derive from my data? And what kind of questions can I answer from the data that I have? And that from that information, what knowledge can I derive? Again, why am I doing all that? Because I need help in my decision making. I am a manager, I am a researcher, I have to make decisions. What can the data tell me? So we move from data to information, from information to knowledge, from knowledge to insight, and from insight to wisdom. So we keep on improving our understanding of the world around us using data. So all this we studied last time. So as the increasing context, increasing complexity, we go from data to understanding relationships, understanding patterns, and then finding out principles. So wisdom would be around principles. And we said that we are yet to reach that stage using the data, right? Like the Buddhahood stage. So we're not claiming to be here as of now. We are in these stages from data to information to knowledge. And we also said that there were 3 events in our environment that have made data science and machine learning and artificial intelligence as trending now. And the 3 were that we now have massive computing power, we have ability of massive data availability of massive data, and we have tools like algorithms, like logic, like statistical tools, like mathematical tools, all these thinking and logic that will help us derive information from data with us. And so we can use all of these. We had statistical means. For example, in our session, we'll be studying about linear regression. So linear regression has been around for more than 150 years or maybe more. And all the mathematics and statistics and logic that we will be using, some or the other part of it has been there with us for ages, maybe thousands of years, that we are all putting it together. But we did not have so much availability of data at any time in history earlier, and we did not have the kind of computing power we have now. So we've really made progress in the last few years, especially if we talk about computing power, especially in the last decades, and moreover in the last 5 years. A lot of how to handle that massive data, because we have gone from computing in terms of CPU, we were doing in terms of CPU to GPU. So we shifted from CPU, not just shifted, we are still using CPU kind of processing unit, and then we also used GPU, and now we use TPU also. So we are using all these kinds of 3 kinds of processing units. So we will be talking about these processing units. And so this has really thousands of times increased our computing power. With the same amount of resources and time, we are able to speed up our processes thousands of times. And that basic change in paradigm shift in our processing basic unit has helped us and given us massive computing power. So that's what we discussed so far last year, and we have massive amounts of data because now we have the internet, we have mobile phones which capture data all the time, and everyone has it. We have digital devices, in our cars, in our watches, in our homes, in all our devices. We have sensors. We are now active on social media, generating and gathering data almost all the time, right? And we have also now the cloud computing, we have parallel computing. So all these improvements, all these innovations, all these happenings have changed the whole ecosystem and brought it to a point that we now want to analyze data, right? So this is what we did last time, right? And then we had stopped actually on this slide. We discussed that what is statistics, and now that we know that we have to do data science, we're calling it data and we're calling it science. So science would be the logic or the way in which we handle data. So what are the tools used in data science? And data science as a term has been coined very recently, and it has come out as a separate discipline. Earlier, like we mentioned, that we had derived statistics from mathematics, just like we derived finance from economics. So now we are deriving a new faculty, a new field called data science. So the very fact how to handle data requires its own set of rules and policies and thinking and thought pattern, and that's why where this subject is coming up. Now, this is not a standalone subject. It comprises of 3 and 4 pillars. The first pillar is computer science. Second pillar is mathematics and statistics. Third pillar is business, to which the problem generates. And the fourth is my communication and visualization tools. So all these together make my data science it's an interdisciplinary field, and it is focused on extracting knowledge from data sets. So what is the field about? It is about extracting knowledge. These data sets, which are typically big data. Again, we'll define big data. What do we mean by big data? How big is data is called big data. And it incorporates skills from computer science, mathematics, business, and communications. Now, many statisticians argue that data science is not a new field, but rather another name for statistics, right? Others argue that data science is distinct from statistics because it focuses on problems and techniques unique to digital data. So both kinds of arguments are there. Statistics forms the base of data, but if you ask me, after being a data scientist and looking at data and handling data, that data science has gone beyond statistics. Again, how have they gone beyond statistics? Because when statistics as a concept, as a theory was generated, it did not have so much data and computing power. So now the assumptions, for example, when we use models in statistics, we say that the data is normally distributed. We assume, but no longer in our models we need to do that. We have models which do not assume any distribution. Why? Because we have so much data, we have computing power, we can always go to the data and make our own distribution, test what distribution it follows. And we have now models which are based on logic that do not require any distribution. And that is why we say we have gone beyond statistics. So once you are aware, you will be using a little bit of statistics and a bit of other things. You can decide on your own whether data science is a new field or is it an extension of statisticians, and make your own opinion, right? So this was a recap of our last class. Let's go forward now. Now, we're still trying to understand what is data science, what is machine learning, and what is artificial intelligence. So we'll try to understand new terms today. Last time, we also looked at terms called data analysis and data analytics. So we looked at data analytics and data analysis. Again, because this is a new field, the terms are not yet very hard defined in watertight compartments. So at some places, they might be used, one might use for the other, sometimes interchangeably, because industry and academia is still in the process of defining a lot of terms because new ideas are cropping up and we are putting that into practice. So, but broadly, we are trying to define the terms as we go forward. So data analysis would be analysis of past data, and data analytics would be using the past data to predict future. So analytics would be taking a step forward. But to do data analytics, you require data analysis, because from past data, we make use of past data and assume that past will continue in the future, and we try to predict the future. Okay, so what is data science? We're trying to understand data. And to understand data, we now have some new concepts like artificial intelligence, machine learning, and deep learning. We try to understand all the three. Now, in artificial intelligence, what is artificial intelligence? The name itself tells us intelligence, which is artificial. We always related intelligence with human beings. Now, if some machine is able to replicate human intelligence, we call it artificial intelligence. So what we are trying to, what is the concept in artificial intelligence? That to enable computers to think, because we are intelligent because we can think. And we are also intelligent because our mind processes information, and we have tools to gather information. So what are our tools to gather information? Our five senses. We can touch, we can smell, we can see, we can hear, and all these inputs go to our brain, and we process data and come out with the decision. And that's what we want that computers should do. And we are able to do so many things on our own by processing, right? So that was the whole idea. Now, this idea was very, very vague. You know, we wanted computers to think, machines to think. But how? How do this was a general concept, okay? So how do we implement it? So machine learning was the part to implement. So this is the broader concept, and the machine learning is the next concept, right? So what is machine learning? We have statistical tools to learn from data. So what we are trying to do is we are learning from data, and the machine is learning from data on its own. What do we mean by that? We'll see as we go forward. And then under machine learning, we had a concept called deep learning. And deep learning are actually neural network. We said machines learn. But when machines are learning, can they learn in the structure, or can they learn by getting inspiration from the way my mind works? So what does my mind has? My mind has neurons. Okay, so this is a neuron. Okay, and not just one neuron, but we have a network of neurons. So we have, how many neurons and message transfers we have in our brain, like trillions of transfer of messages. So one neuron transfers message to various other neurons, and they're connected by various other neurons. So information is coming all the time to these cells, and they are transferring information all the time. So there's a network of this is a neuron, this is a neuron, this is a neuron. So people said, can I and we are very complex in our decision making. We can do very, very complex functions, and a lot of times with very little supervision, we are able to do new things. We are able to be creative and innovate and make our own decisions when nobody has told us anything, by observing, by thinking. We just sit down, think, and a new thought comes to us, right? So using this inspiration of a network where information is passed from one node of a neuron to another, can this be replicated in machines, and can we do that in decision making, was what inspired deep learning. And now in the last 4 to 5 years, when we have shifted, as we mentioned, from CPU to GPU to TPU, data processing units, as a processing unit, we have really drawn some excellent work in neural network, and they have become very, very powerful to decipher things around us. So this is how it goes. Again, let's define a little bit more. We saw that artificial intelligence is the bigger concept, and all of it is data science, because everywhere we are trying to find out what is the intelligence we can derive, what is the information, knowledge we can derive from data. So data science is the extraction of knowledge from data by using different techniques and algorithms. And artificial intelligence is a technique which enables machines to mimic human behavior. We're trying to make them as humans. And what is machine learning? Which is a subset of AI technique which uses statistical methods to enable machines to improve with experience. So machine learns on its own. Okay, what does that mean? Once we do, and once we learn an algorithm, then this statement will be absolutely clear to you. And what is deep learning? Again, is a subset of machine learning. It's a technique, one of the techniques in machine learning, which makes the computation of multi-layer, not just one layer, but multi-layer, just like our brain, neural network feasible, right? So far, is it clear so far? A bit of it?
Yes, ma'am.
Yes.
Okay, great. Now, artificial intelligence, let's just spend a few minutes on it before we move forward to define other topics again. So artificial intelligence, again, like I mentioned, we are still progressing, we're still seeing what definitions we can give to different terms and how do we come to a general conclusion. And we saw that in artificial intelligence, currently we are in the narrow or weak AI stage, which has narrow range of abilities, which means that if we have a Siri or an Alexa or a Cortana, okay, these are virtual assistants, they can do only certain specific roles that they have been programmed to do. So if Alexa has no information, has not been fed information about, say, cooking, and I ask Alexa about cooking, it won't not reply. Again, Alexa cannot help me in driving a car. Alexa cannot help me in doing statistical analysis. Alexa is not Python. So what one machine learning or machine tool can do, the other cannot, right? So it's called narrow range of abilities. Whatever tools we are developing in artificial intelligence and machine learning, they can do only one thing for which they've been programmed. So like Watson's, IBM's Watson's, or facial images recognition. Now, Alexa cannot do facial recognition. It can do voice recognition, maybe, or it can answer my questions. Then disease mapping. Alexa cannot do disease mapping. That's another algorithm that we have to make, and prediction tools. Then manufacturing and drone robots. Then email spams. Now, again, what email spam filters can do, they can't do facial recognitions, right? So what means here is that each tool is separate and they have own domain of work that they can do, and they cannot learn the work of some other machine tool, like entertainment or marketing content recommendation. So what is recommendation engines? What you see or which recommend you to watch something, like in Netflix, if you're watching a movie, then you will have similar movies recommended to you. Or if you're going to Amazon and you have say you purchase a t-shirt, then you will be recommended other t-shirts which are of similar color and similar style. Or if you're buying a book, then you will be recommended that somebody who bought this book similarly bought other books. So a market basket analysis would be done, or other books would be recommended, other subjects that, people like you who bought this book also read other books of these domains. So these are recommendations engines for purchase behavior. So if you're buying, say, bread, they will recommend you buy butter also. If you're buying butter, they recommend you buy a butter knife also. If you're buying butter knife, they're saying recommend you buy a cutlery also, right? And then self-driving cars. So all these examples are of weak or narrow AI, but here also we've made tremendous progress, and in all our works of life, I'm sure all of you are using this, and our cell phones are full of machine learning applications, as you all know. Then we come to general or strong AI, which is stronger than the narrow AI, which is on par with human capabilities. So we are saying that artificial intelligence, machines with general intelligence, which mimics human intelligence or behavior, with the ability to learn and apply its intelligence to solve any problem, right? So what we are saying is, when machines becomes like us, they can learn on their own, and AGI can think, they can understand and act in a way that is indistinguishable from that of a human in any given situation. So there is a test called Turing test. So there was Alan Turing in the 1960s. So he devised a test, and he said that if suppose I am talking on the phone, and on the other end, whether it is Alexa answering me or whether it is a human being answering me, and I am not able to figure out whether it's actually a real person or it's a machine tool like Alexa, then that machine tool has passed the Turing test, which means that they have come up to the level of human capabilities. We have not yet reached there. We think, but we are struggling at this stage. We've not reached the human level of intelligence, because here we need consciousness, we need human intelligence, thinking, and not just that the machine is programmed to do a certain job and they cannot do the other job. So if you are doing facial recognition, then you can't do recommendations. So the point here is that you can do both, and we have not yet implemented any machine that can do both on its own and learn and improve on its own going forward. So here we've not reached any level of general or strong intelligence. We're still in the weak stage, although we've made a lot of progress here. And then comes artificial super intelligence, ASI. This general was AGI, right? And weak is AI. So super intelligence is when when machines go beyond humans, which are more capable than humans. For example, we cannot find out the magnetic space, like whales and birds. Sometimes they can find out their position and then navigate through long distances over the world. They can go from northern hemisphere to southern hemisphere. They can migrate over continents. Whales can also hear ultrasonic sounds. All those capabilities are not there in humans. So can you develop machines which are capable of more than human? Then that would be artificial super intelligence, and that this part and this part, we're still in the fiction stage, we're just writing about it. So is it fine? Can we go forward? This is understood so far?
Yes, ma'am.
Okay, great. So now let's look at a little more in depth about machine learning. So machine learning, let's understand how is machine learning different than traditional learning. So in traditional learning, what would we do? We will have a program data, and we'll have our program. So we will have some data and we'll write a program on it, right? So for example, we'll say x is equal to 2, y is equal to 3, z is equal to x plus y, and we will and print z. So this is our program. So we will feed this program in the computer. So we have the data, we have the program, and we run it on the computer. And so we would say print z, it gives me 2 plus 3 is equal to 5. So it gives me the output 5, right? Now in machine learning, we are not giving the machine the program. What are we giving? We're giving data. So we're giving x is equal to 2, right? And y is equal to 3. And we are giving output also. We are also saying z is equal to 5. And we're giving this whole data, the output also, to the computer. And the computer gives me a program that z is equal to x plus y. This program comes out, then that becomes machine learning. Is it making some sense?
Yes, ma'am.
Right. So I'm not telling the computer what is the formula here, what is the program here. Okay. It is making the program on its own. Let's look at one more example here to make you understand things better. So right. Yeah. So if you see here, we have some data. We have some x and we have some y, right? Now, in a program, in some other traditional program, what will we do? We will write down the program. We will say that if we want to find out, if you want to see, y is my output. So y would be my output, and this is my input. So if I want to write a program that if I give the value of input, they should give me the value of output. So what will I do? I will write a program that if x is equal to 2, y is equal to 4. If else if x is equal to 4, y is equal to 8, and so on. Am I right? You write programs like that? Am I right?
Yes, ma'am.
Right.
Yes, ma'am.
Yes. So we will write this program, and that's my traditional way. That's my traditional way. So if you go and ask this program, what is the value of y? What is the value of y when the value of x is 12? So what will it go? It will go and run in this loop and go through all the ifs and if-else statements and find out where x is equal to 2, what is the value of y, and give you the output 24. Okay. Now, this would be traditional. What do we do in machine learning? What do we do in machine learning? We do not provided these set of rules. We provided the input and the output. That's what we said here in our discussion. That we provided data and output. So what are we providing it? We're providing it X and we're providing it Y. And we're providing the computer these two. And what is the output? It gives me the relationship. It says Y is equal to 2X. Now, if I ask it, what is the value of Y when X is equal to 18, it will keep this value in here. So it will say Y is equal to 2X is the output or the model that has come out of my computer or my machine learning attempt, and I gave it X, I gave it Y, it gave me this model. So now if I ask that what is the value of Y if the value of X is 18, then all I have to do is 2 into 18 is equal to 36, because it established the relationship between Y and X. I can make any kind of prediction I want. Is it making sense?
Yeah, ma'am.
Right. So how did I do that? How did the computer do that? Because I gave it an algorithm. And what was that algorithm? I said that you build a linear regression model, right? Build a model which has two parameters. Y is equal to mx plus c, where c is the intercept, m is the slope. Calculate the slope, calculate the c by using some formula, put it there, find out the difference from the actual, square, sum it up, find out this will call it cost, compute this cost for various values of m and c, find out where the cost is minimum, and that value of m and c, make it as a model. Now these are steps of the algorithm. Okay. Now even if I change this data somewhere, so this becomes machine learning. We will be doing this in detail in this whole page. We will be studying each and every formula in our next session, next Tuesday. We will be doing this, but before that we need to understand the data, and that's why we are understanding what is the type of data and what is data. But I wanted to show you this so that you become clear that what is the difference between traditional and machine learning, and not just conceptual. So just to make your understanding a bit, that I brought you on this sheet in this session. So now suppose I change this. I suppose change this from 9 to say 17. And so this program changes on its own. So if I change the value of this program changes on it, the whole thing changes on its own, right? So I can input any value. But if I was doing the traditional method, I will have to change this program and say that when x is equal to 17, y is equal to 16. I'll have to hard code it. Here I don't have to hard code it. It automatically changes the model. Is it making sense? It didn't change here because the data is linked to this value. So if I change this value, suppose I change this to 14, so see, everything changed. Everything changed here now. And this graph did not change again because this graph is linked to this data, and this I have linked to this. So I should link it here. So what I should do is I should link this to this, and then everything will be connected. Right, plus y, but I had set the data in certain ways, right? Okay, Did you see that everything turned? Yeah, this also changed now because this graph was linked to this data. So if I change this to say 20, so then everything changes. Yeah. No, sorry, I should change it here. I should change it here. So if I change this to 20, then everything changes. See, the whole thing changes. So my model automatically changes. But I cannot do the same in the traditional. Is it making sense? I'll clean this whole thing up and come back in the next session and explore it further. Is it making sense?
Yes,
So,
ma'am.
Yes.
okay, now again, just to describe the machine learning process a bit further, because when we learn this whole model is called the linear regression model. We will be using this model to understand all the steps of machine learning. Okay, this seems a little more clear. We will be understanding what is the cost and loss function in machine learning. How do I come to this formula? We will be understanding all these steps. Okay. So we will use linear regression, which we will do in Excel and also in Python. And so we'll use linear regression to understand the machine learning steps. So what is the machine learning? Machine learning steps are, or machine learning, it's called machine learning steps or machine learning pipeline or machine learning process, whatever you want to call it. Its first is to define a machine learning problem and propose a solution. You want to say that this is my data set and I want to find out the relationship or the pattern. And so that if I have these numbers and I have another number, 28, how do I predict what is the value of y? I put any number here. Can I make a prediction what will be the value of y? Learning from this set of numbers when I give to the computer. And if I change this, any number here, this should also change, right? So I define a problem. Then what I do, I construct your data set. So for this problem, what data set do I have? Is it x equal to 2 or is it x is equal to 4 and then y is equal to 8? Whatever the data set is, then I have to define my data. So I have a problem, I say I want a solution to it, and this might be the solution. Then I construct my data set. Then I transform my data. I make changes in my data. I clean my data. These are broad steps, but under this, there are a lot of sub-steps also. So how do I construct my data? Do I already have existing data, or do I buy data from third parties, or do I gather data? So do I have the digital data? Digital data I already have that I've collected, or do I generate data through interviews or questionnaires, okay, or any other form, or I buy data. Buy data from third party. Okay, so how do I get the data? So once you construct your data, in this you will also mine your data. Maybe you have, say, 1 billion records. You don't need all 1 billion. You need a subset. So you did data mining and get your data, and then you transform your data. So you clean your data. Okay, you understand your data. Clean your data, you change if there are missing values, there are outliers, so missing values, you treat those missing values, there are outliers in the data set, okay? So you then you understand your data, okay? What exactly is the data telling you? Then you transform your data, okay? The data transformation techniques. What do I mean by transformation? I mean that if it is in text form, you convert it into numerical form. If it is, if the data is too large, for example, if the information is in crores of rupees, can I convert it into, say, lakhs or thousands? Can I convert them into smaller numbers, like you do in say, balance sheets? So can you normalize the data? So I normalize data. There are various techniques of normalization. I standardize the data, okay, and then once I have done that transformation, I can do data, I can do feature engineering. I can create more features out of the data. Okay, I create some new features. For example, if I have GDP and population size, so I will calculate a new column in my data set called GDP per capita. because GDP per capita is a ratio and provides me more information. I can now compare the GDP per capita of, say, America and India. So I create more features. So this is a feature of my data. This is a feature of my data. This was not there. I created it, right? And then I trained the model. So I built an algorithm. Like, we will be studying the very basic linear regression. So I build that algorithm, and then I use that algorithm to make predictions. Okay, I tune that algorithm. I evaluate the model. How is it a good model? How do I evaluate? I find out its accuracy. I calculate its accuracy, and then I use that model to make predictions. Just like we are saying that once we have this model ready, once we have this equation. What is a model? This equation is my model, where I have found out the value of M and C, and then I predict that, okay, given this data, see, I'm using this, given this, how do I find out? So I'm using this 0.9465, so 0.9465 into 28, the value of X, plus the intercept, 7.046. So I'm using this to predict Y for any value of X. So then I make prediction, and after that, then I use that for my general use. I use this model, and we call it deployment. So then I deploy my model. So for example, Netflix makes a recommendation engine, and then it deploys that. And as users, when we go to their site, we can make use of that. It actually generates recommendations for me. Is it making sense so far?
Yes, ma'am.
Any questions you have?
Oh,
Okay, great. So again, types of machine learning problems. It could be a classification problem, which says whether, pick one of the labels, whether a picture is of a cat or a dog or a horse or a bear, or whether it's, cancer is benign or it is malignant, or any kind of classification, whether the person is a fraud or not, whether I should give loan to that person or not, whether he will default or not. So classify. Then the regression would be the answer is in the form of a variable. I predict the number. What will be the GDP of the country next year? Okay. What are the factors that affect GDP? Right. Or for example, in our example, what will be the value of Y if X is given? So this is a number. So when it is a number, we say predict numerical values. It is called regression. And for example, how many click-through rates on the website? How many clicks can how do we predict that? That builds regression. Then clustering. Another type of problem that machine learning does is clustering. So for example, similar examples. For example, if you Google news in Google, if you say Google, if you go to Google News, it has clubbed all the news of each topic together, and you can, for each of the events that has happened in the world in the last few days, last few hours, it will have, say, 100 news items presented to you, right? Or when you do search engine, okay, search engine is a very good example of clustering. It clusters all the sites that are similar and provides you the search results. Okay. Or in marketing, if you do clustering, you do segmentation, which customers are similar in nature. So that's clustering. Then association rules. Infer likely association patterns in data. If you buy burger buns, you are likely to buy hamburgers. So this is unsupervised learning. So this is called unsupervised. This is called unsupervised learning. And then structured output. Create complex output. Natural language, parse trees, image recognition, bounding boxes. So all these are types of machine learning applications. Okay, we will be only doing linear regression because we have only 10 sessions, but it will give you a very, very fair grounding in machine learning and what are the basic features. So if somebody understands linear regression from the perspectives of machine learning, then all other algorithms you have already learned. You have already learned what is a loss function, what is optimization techniques, and so for any other algorithm which are used in classification or any regression or clustering, you are able to quickly come to terms with all the features of the machine learning problem, right? So that's why we all start with linear regression, which is just building a line. If you look at it the other way. So then we'll just discuss this last slide today. Here we are saying that, we said statistics is a tool, starting tool of doing data science. And so statistics also has come a long way from being a descriptive statistics. We're just describing the data. We're just looking at the data. And then next step is inferential. So we move from data to information. So we use inferential statistics. And then from inference, we go to predictive statistics. And then from there to prescriptive statistics, right? So descriptive statistics simply describes the world as it is. In predictive statistics, we ask questions. What will happen if we change our prices? Can we predict if more or few people will buy the product? Is there an element of uncertainty that simply calls beyond going or describing? So in descriptive, we say what happened. Okay. In predictive, to say what will happen. Why will it happen? Okay. And in prescriptive, we say don't just predict, but tell me what should I do? What should I do? Why should I do it? Right? So these are advanced analytics. We are reaching here, but mostly we are doing predictive and descriptive. You cannot do predictive unless you know your data. And for knowing your data, you have to do descriptive analytics. So we will be doing a little bit of descriptive, a little bit of predictive. So like we said that we are predicting Y from X, right? So that would come under predictive statistics. Right here also, how do we predict? We have historical data, we make an algorithm, we make a model, we use new data, we have new data, we have the model, and we make predictions. Just like we have here, we have historical data, right? So this is historical data about X and Y. We have a predictive algorithm. What is the algorithm? To make this Y is equal to mx, and you have to optimize it for reducing the cost function. These terms I will be explaining again. So that is our model. This is our data, right? And from that data, what do I get? I get a model. And what is this model? This is the model I get. Y is equal to mxc values I get. So I have made a model. And then I have new data. Now I have new data. I have data x is equal to 28, which is not part of this previous data. And I say, I use the model and I make a prediction. And that's what we're using here. We use the model and say, use this equation and make a prediction that given a value of x, the value of y should be 33.5. Is it making sense? Can we stop here today?
Yes, ma'am.
Okay. Good. So let me start.